Okay, ladies and gentlemen, let's take a look at ratio and proportion. Now, obviously, a ratio compares two like things. Two like things. Okay, now, to compare two like things, for example, let's say I have a geometry class, and in my geometry class, I have 28 wonderful students. And in Miss Deals, I think I misspelled Miss Deals. Whatever. Okay. She has 31 bright and shining students. Okay. So the ratio of my classroom to her classroom as far as students goes is 27 to 31. So the ratio is 27 to 31. Now, again, students to students, they compare like things. Now, let me give you something that is not a ratio. So ratio, no. That would be $1.79 for 1 gallon of gas. That is not a ratio. Now you say, well, but they're both fractions. Yes, they are indeed. You say, yes, but as one of these goes up, something else goes up, and that's in fact what makes it a rate. This is a rate, ladies and gentlemen. A rate is usually comparing two unlike things. In this case, a unit of money to a unit of volume. Versus over here, our ratio is students to students, okay? Now, another way we could say it is we could say in my classroom, there are 13 boys and there are 14 girls. And you say, Mr. Moore, wait, that's not possibly a ratio because I know from health class that boys and girls are different. And the answer is, I understand what you're saying, but however, we are still comparing people to people. So when we're comparing things, we need to be careful that we are looking at ratio and proportion from a perspective. Whereas, are these things really in like terms or not like terms, like cost to volume? Now, let's put it in a geometry context. In a geometry context, I can have two squares. Here we go. Square, square, square. Now, I know that because of all the tick marks and all the little right angles. That's a square, that's a square, that's a square. And this has sides of 6, 6, 6, and 6. This square over here, you'll notice they're all the same mark, but they are different because this is not the same size as this, even though all sides of this are equal among itself. So this square here, you have 1, 1, 1, 1. The ratio, ladies and gentlemen, the ratio of these two squares is, and of course the answer is 1 to 6. Now I could write it 1 to 6, I could write it 6 to 1, because here's the thing. It still compares like things whether I say 13 boys to 14 girls or 14 girls to 13 boys. Now, they are different ratios, but they are equivalent because they are measuring the same groups of items, so 1 to 6. Now, I could also write it as this, 1 to 6. That could be a ratio written with a TO in the middle. Also, you could say 1 over 6. There you go. Now, of course, this ratio is already simplified. So is this one, and so is this one. But if I had something that was, say, 3 to 12, 3 to 12, you could reduce them and say 1 to 4. So that would be a ratio in lowest terms. We traditionally want to do ratio in lowest terms. By the way, these two figures, although they are both squares, they are not the same size, so they cannot be congruent. They are not congruent at all. In fact, what they are is they are wiggly equal sign, also known as similar. These would be similar, and similar figures have congruent angles, but proportional sides. Now, by the way, that has to be true for every single side. 6 to 1, 6 to 1, 6 to 1, 6 to 1. For all sides, they have to be the same. Now, we could do an extended proportion. We could say in this triangle, the ratio of the angles is 2x to 3x to 4x. What that means is, if I were to take these and add them up, 2x plus 3x plus 4x, they would have to equal, anyone, 180, because it's a triangle. And so we could put all these together and come up with 7, 9x equals 180. x equals 20. So that means this angle down here is going to be 40, and this one's going to be 80, and this one is going to be 60. Does that make sense? Yes, it does. Okay. So what we can do is we can write an extended proportion. That extended proportion would be 40 to 60 to 80. Or, of course, we can reduce it to be 4 to 6 to 8. In fact, we could even reduce it further if we wanted, but let's not go there. In this case, since we know they were in this ratio to begin with, even without solving it, we could have said the ratio is 2x to 3x to 4x. Okay, 2x to 3x to 4x. And if I were to reduce this, I would indeed get 2, 3, 4. So this is an extended ratio because it compares more than two things. Now, obviously, you can't write that as a fraction, but you can write it in the 2 form, 2, 2, 2, or with the colons. Now, the way you take ratios and the way they're useful is if I know that this figure is proportional. Let's start over. If I know ABC, triangle ABC, is similar to triangle DEF, and we'll keep it simple here, folks. DEF. Oh, wait a minute. ABC. So well, let's keep it simple. DEF. There we go. Okay. And we know that this is in a ratio. This is a side of 2, a side of 4, and a side of 3. I think, yes, that makes a triangle very nicely. And I know that this is 9. My question is, how do I find x and how do I find y? Well, a ratio is good because I know the sides here have to be in a ratio of 2 to 3 to 4 or y to x to 9. So we have 2 to 3 to 4. And we have that would have to equal y to x to 9. Now, the nice thing is I can find the missing pieces by equating some things. I know that the 4 and the 9 go together. So I can say these triangles are in a ratio of 9 to 4. But that means if I try to find y has to go with 2. It's very basic proportions, just like you have done in junior high, you've done in algebra 1, or you've done in pre-algebra. So in this case, this is a proportion because a proportion, unlike a ratio that compares two like things, a proportion compares two ratios. All right, so all I got to do is cross multiply them, and I get 18 equals 4y. And if I have 18 equals 4y, divide both sides by 4, and I come up with 9/2 equals y and or 4.5. Now see if that makes sense. 9 is to 4.5 as 4 is to 2. Well, yeah, it's half as big, and I could do the same thing. So I want you to go ahead and find x and turn that in. Okay, so that is ratios and proportions. Let's go a little bit crazier. What if I have these two figures, A, B, C, D, E, F, and again, A, B, C is similar to D, E, F. Okay, and this is labeled x plus 1, and this is labeled 3x, this is labeled 4, and this is labeled 2x. All right, we have something like this. A to B to C, D to E to F. Okay, so let's set up a ratio and a proportion. This ratio would be x plus 1 goes with 4, as 3x goes with 2x. Now that's one way to write it. By the way, we could write a proportion multiple different ways. Instead of comparing here to here like terms, could I compare side to side and the same side to side order? So I have x plus 1 is to 3x as 4 is to 2x. this to this, this to this. Yes, it works the same way. In fact, I can prove it to you because again, we're going to cross multiply. And we're going to end up with 2x squared because x times 2x is 2x squared plus, don't forget to distribute, 2x equals, and you end up with 12x here. Now, to solve this, of course, you would do what? Get everything to one side. So I have 2x squared plus 2x minus 12x equals 0. 2x plus negative 10x equals 0. All I have, x squared, excuse me. All I have to do now is what to solve? Well, let's factor. Let's take a 2 and an x out, leaving x minus 5 equals 0. 2x equals 0. X minus 5 equals 0. That's algebra. You're expected to be able to do that. And so x equals 0, x equals 5. Now, obviously, x can't be 0 because that would make this a side of 0, a side of 1, a side of 4, and a side of 0. That doesn't make any sense. So that can't be right, but I could use the 5. So that would be 6 to 15. And this would be 4 to 10. 6 to 15, 4 to 10. Yeah, that actually works out. Your job is to prove that this also would equal the same answers. So go for it. Do that one there. While we're talking, we have to talk about a couple deals. These two terms here in this position, the lower left and the upper right, are called the means. And these two terms here, the upper left and the lower right, are called the extremes. So the means and the extremes, you multiply them together. So those are the names of the things. So let's see what you can do. You have this and you have the other x that you need to find and be able to turn in. So that is the homework component, is to finish that.